we're just going to talk through a crash course on quantum computing. And the first thing that we're going to do is take everything you already know about classical computing in the context of Boolean circuits and just map it to matrix multiplication and vectors. And it turns out that this is a really good formalism for how to think about quantum computation. So the first step is to think about states as vectors, as column vectors. So if we have just a normal classical bit, it's either 0 or 1. And we're going to represent this as a column vector with two entries. The 0 state is a 1, 0. The 1 state is a 0, 1. If we have 2 bits, then we have 4 possible states. So it's going to be a column vector with 4 entries. The top entry is 0, 0. The bottom entry is 1, 1. Which means that if we want to represent the Boolean state 0, 0, we have the column vector 1, 0, 0, 0. If we have 0, 1, it's the column vector 0, 1, 0, 0, and so forth. And you can see that if we have n bits, then the state vector for n bits is a column vector with 2 raised to n entries. So that covers states. The next thing is how to implement gates, Boolean gates. And we think of Boolean gates in this formalism as matrices. So the simplest gate is just the NOT gate, which takes a 0 and turns it into 1 and vice versa. So in our notation, that's what it looks like. And this actually tells us that the NOT gate is a 2 by 2 matrix that looks like this, 0, 1, 1, 0. And you could verify that by plugging this into the 2 equations on the left. As another example, the AND gate takes 2 inputs and has 1 output. Here's the 4 cases. And the only case where the output of the AND gate is the 1 state, or the 0, 1 column vector, that's in the bottom right. And that's where the input vector is 0, 0, 0, 1, which is the 1, 1 state. So this tells us that the AND gate has 2 rows, 4 columns, and only the right column is where you get the Boolean 1 output, which is the 0, 1 column vector. So you can convince yourself that you can apply this reasoning to take any Boolean circuit you've ever seen and think of it as matrix multiplication applied to column vectors as states. It's not a particularly useful way of thinking about Boolean computation because you're just going to have state vectors that have 1, 1 and just the rest zeros. But it is an equivalent formalism for thinking about Boolean circuits. And the reason that we think about it this way is because when we move on to quantum states, a quantum state can be 0 or 1, but it can also be any point on this sphere. So we still have the 0 state, which is represented as the North Pole, Santa Claus. That's the 0 state, again, 1, 0 as a column vector. And we have a South Pole, which is the 1 state, represented again by the same column vector, 0, 1. But any other point on this sphere is also a valid quantum state. So as an example, if we take the intersection of the equator and the prime meridian, we get the state that's called 0 plus 1. I'm going to skip the root 2 normalization factors because it's not too important. But as a vector, this would be represented as 1, 1. And if you've ever heard of Schrodinger's cat, the thought experiment, this is exactly Schrodinger's cat. It's half dead, half alive, half 0, half 1. And what that means in physical terms is that if we measure it, there's a 50% chance that we get 0 and a 50% chance that we get 1. So a quantum state, just to reiterate, a qubit, quantum bit, can be any point on this sphere, not just 0 or 1, which is why our state vectors become a lot more interesting. And the key point that I want to drive here is that on the right we have something called a superposition. It's a superposition of the 0 state and the 1 state at the same time. And the power of quantum computing comes from the fact that superpositions compose in interesting ways. So as an example, if we have 2 qubits that are both in the 0 plus 1 state, then you can just multiply that out like normal math. You get 0, 0 plus 0, 1 plus 1, 0 plus 1, 1, which would be represented as the column vector of all 1s. If you had 3 qubits, you'd have all in the 0 plus 1 state, and you multiply that out, you would get every possibility from 0, 0, 0 to 1, 1, 1, which is a column vector with 8 1s. And the key takeaway in quantum computing is this. A quantum circuit will operate on each of these states at the same time in parallel. So with classical computers, when we have the state vector, we do have this property that n bits correspond to a state space of 2 raised to n elements. But the problem is we only operate on one of those elements at a time. With quantum, if we have a superposition of 0 and 1 for each qubit, then the composite state will span every single state in our state space. And this is kind of the, I should caveat this, that this is kind of the popular science description of quantum computing, that you operate on all these states in parallel. And that is one of the 2 elements that makes quantum computing fast, potentially. But there is this second element that you also need wave interference to really make it matter. Otherwise, you just get random results. That part isn't really necessary to understand this talk, but I will just stay true to the science and mention that. But it is useful just to think about the fact that superposition gives rise to this state vector that has 1 in every position. We operate on all those states in parallel, which is part of where quantum gets its speed up from. So now let's talk about, we've talked about quantum states as state vectors. Now let's talk about the gates that we can use to operate on quantum states. So in the classical model, the only 1-bit gate was the NOT gate. In quantum gates, we have for a single qubit, these are 3 of the main gates that are used. They correspond to rotations on the sphere on either the x, y, or z axis by an angle of theta degrees. And what you'll note here is that the coefficients in this matrix are not just 0 and 1. They can be fractional numbers. They can be complex numbers, imaginary numbers. And one gate in particular that I also want to highlight is called the Hadamard gate. This is what it looks like, 1, 1, 1, negative 1. And the reason I want to highlight it is because it can create superposition. And what I mean by that is if we pass it as the input, just the 0 state, which is the column vector 1, 0, the output is 1, 1, which is a superposition of 0 and 1. Similarly, if we had the 1 state as input, then we'd end up with 1, negative 1, which is 0, minus 1. So Hadamard creates superposition. There's also a 2-qubit gate that I want to talk about that's very fundamental, called the C0 gate, which stands for controlled NOT. This is what it looks like in a circuit diagram. And what it means is this. The top qubit is a control line, and the bottom qubit is a NOT gate that is activated only when the top qubit is on. So in other words, if we have as input 0 on top and x on the bottom, that means that the control is off. It doesn't do anything. It just stays in 0x. But if we have a 1 on the top and an x on the bottom, then we flip the x and we maintain the 1. So we end up with 1 and not x. So this gate description gives rise to this matrix description. The left 2 columns are the case where the control bit is 0, and then it's just the identity matrix. But on the right 2 columns, we have this flip behavior, because that's where the control bit is 1. And what I want to highlight about the C0 gate is that it can create something called entanglement. So let me show you an example. Let's say that the top qubit is in this 0 plus 1 superposition state, and the bottom qubit is in the 0 state. So if we write out that composite state as a state vector, we have 1, 0, 1, 0. We do the matrix multiplication, we get 1, 0, 0, 1, which is 0, 0 plus 1, 1. So what do I mean by it creates entanglement? Well, in the input state, I gave you a description of the quantum state as being 0 plus 1 on the top qubit and 0 on the bottom qubit. But in the final state, the entangled state, we have 0, 0 plus 1, 1. And there's no way to factor that into a description of a separate thing on the first qubit and a separate state on the second qubit. You might be tempted to think that it's 0 plus 1 and 0 plus 1, but if you did that multiplication, you'd end up with 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. All we have is 0, 0 plus 1, 1. So the C0 created a situation where the resulting state can't be described as individual components being composed. It's a system unto itself, where we have to think about both qubits as being part of a system. And that turns out to be very critical for quantum computation. So I'm going to skip the example till after the break and just summarize really quickly. So again, in quantum computation, we think of states as being represented by column vectors, and the gates that operate on them are represented by matrices. The quantum states can be in these superposition states. You saw those vectors of all ones. And that's part of where we get the speed up of quantum computation. If you have n qubits, you're operating on a 2 raised to n state space. And then finally, the C0 is an entangling gate, which we'll see in the demo after the break. So the rest of this talk is just a quick example of a simple quantum algorithm to kind of drive these concepts home. I understand that they're probably a little bit foreign if it's your first time seeing it. And then I'm going to talk about the chemistry applications in quantum computation, and then go through a demo of the VQE algorithm, which we'll talk about. So we're going to go through, just walk through this circuit. This is what a quantum circuit looks like, and this implements something called quantum teleportation. So if you put on your tinfoil caps, started, and I'm going to explain what all these pieces mean, but let me just talk about the task. The task is we have 3 input qubit lines. The top qubit is in some unknown state, which is A0 plus B1, and our goal is to teleport that qubit to the bottom line. And this seems like classically a really challenging task because the A and B coefficients can have infinite precision. They have, like, remember, they have decimals, they're complex numbers. And if we measure it, then we're screwed because as soon as we measure it, it collapses to either 0 or 1. So somehow we need to teleport it to the bottom. And it turns out that this circuit does it, and the way we start is by putting the bottom 2 qubits in this superposition state of 0, 0, and 1, 1. It's an entangled state, as we saw from the last slide. Now, before we proceed, right now what we have is a description of the top qubit and a separate description of the bottom 2 qubits. And let's think about this instead as the 3 qubits as a whole. So to get that, all we do is multiply the left qubit descriptions, just like normal math, which means that we end up with A000 plus A011 and so forth. Now, the first thing that our circuit does, actually before that, let's imagine that the bottom qubit for dramatic effect is moved to Mars, and then the top 2 qubits are still with us at the quantum center of St. Charles. So what we're going to do is first apply on the top 2 qubits, the 2 qubits that we own, we're going to apply a C0 gate. That's that first controlled knot thing on the left. And as a refresher, C0 doesn't do anything if the control bit, which is the left bit in this description, is a 0. But if it's a 1, then it'll flip the middle bit. So that means that the A00 and A01 states, no changes because the control bit is 0. The B states, we have a 1 in the control bit. So all we do is take the middle bit and flip it. So 100 becomes 110, 111 becomes 101. That's what happened there. The next gate that we apply is the Hadamard gate, which again has this matrix 1, 1, 1, negative 1. It operates on the top qubit, which is the leftmost qubit in this description, turns a 0 into a 0 plus 1, and a 1 into 0 minus 1. So the number of states then doubles if we plug that in. We have 8 states. The last thing that happens is that we measure the top 2 qubits, and we consider the measures to be controls, classical controls this time, on these 2 gates. The left gate is the NOT gate, and the right gate is the Z gate, but we actually won't need to worry about that one. So there's 4 possible outcomes. The first is that the top 2 qubits are measured as 0, 0, or they could be 0, 1, they could be 1, 0, or 1, 1. So let's take the simplest case, which is that we happen to get 25% chance. We get 0, 0 for these measurements, which means on the top 2 qubits, which means that our entire state only collapses to the 2 states that have 0, 0 in the front. And if we rewrite this and factor it out, we have 0, 0, A0 plus B1. And that's exactly what we wanted. That means that the bottom qubit is A0 plus B1, which means that we teleported the A0 plus B1 from the top to Mars at the bottom. As there's 3 more cases, I'll just do one of them really quickly. Let's say that we measured a 0, 1, which means 0 on top, 1 on the bottom. This prescription is telling us that we should apply a NOT gate. So if we factor out what we have here is A011 1 plus B010, 0, we end up with 0, 1, A1, B0, which is wrong because we have A1, B0. We want A0, B1. But aha, this is where we apply since we measured a 1, we apply the NOT gate, and we end up with A0 plus B1. And then there's two more cases that you could work out. This other Z gate takes care of the negative signs in some of these terms, and the NOT gate takes care of the flipping. So this is just meant to give you some intuition on how a quantum circuit works in practice. Teleportation, by the way, I should add, it doesn't mean faster than speed of light communication, because we still had to tell our people on Mars what they should apply to their bottom qubit. Otherwise, if we didn't tell them, they'd just be stuck on figuring out whether or not to apply these gates, and they'd guess randomly and only get it 25% of the time. So the next thing that we're going to do is talk about chemistry applications for quantum computation. And I'm going to motivate this with a quote from Dirac in 1929, who observed that the physical laws necessary for a large part of physics and chemistry are completely known. But the difficulty is that the exact application of these laws leads to equations much too complicated to be soluble. And this is something that has really practical implications today. There's some statistic that something like at least 10%, maybe more, of the DOE's supercomputing cycles go towards simulation of quantum chemistry, and basically any sort of atomic physics that has quantum principles. So one of these problems that is of interest to chemists is ground state determination. So you might recall something like this from your high school chemistry class, and this is basically the question of how do we assign electrons to addresses and orbitals such that the energy of a particular molecule is minimized. In other words, what is the ground state energy? And it turns out that computationally, we can think of this as an eigenvalue, eigenvector problem. Every molecule is described by something called a Hamiltonian matrix, which captures terms like the fact that electrons have kinetic energy, they repel each other, but are attracted to the nucleus. And the Hamiltonian matrix is just a matrix that encompasses all these terms for a given molecule. And finding the ground state is equivalent to finding the lowest eigenvalue of such a matrix. But the problem is that classically on a regular computer, this has a combinatorial explosion in the electron address space. And it's an intractable problem for classical computers to solve exactly, or even approximately. And Richard Feynman had this disruptive idea that is the foundation of quantum computation in 1982, that, hey, if we want to figure out the properties of quantum systems, we should run the problem on a quantum system. And that's what quantum computing is all about. And it turns out that this idea led to a lot of invention and algorithms, and we found that chemistry problems on quantum computers are tractable. The molecule at the bottom right is cholesterol, and a recent paper proved that, a 2005 paper proved that if we had 1,000 high-quality qubits, quantum bits, then we'd be able to perform an exact diagonalization of the Hamiltonian of cholesterol, which is something that wouldn't be remotely possible with classical computers, even supercomputers. So there's a couple different, the original algorithm for solving these problems was called quantum phase estimation, but the hot thing right now is called VQE, Variational Quantum Eigensolver. And it's good because it can run on near-term devices because it has more modest quantum requirements, and it passes a lot of work to a classical coprocessor like what Fred had mentioned. And it sounds complicated, but all it is guess, check, and repeat. So to recap, the problem is we want to find the lowest eigenvalue of a given matrix. And the first step is to guess what that lowest eigenvector is. So we take a total guess of the ground state vector, and we parameterize that state vector, that column vector that we saw earlier, with a bunch of angles, theta 1 through theta n. And this guess is called the ansatz because we want to sound fancy. And then the second part is to check. Checking means we measure for this potential ground state, what is its energy? What is the expectation value of H, which is that Hamiltonian matrix? So we've done the guess, we've done the check, and then we repeat. We repeat kind of intelligently. We hand off these results to a classical coprocessor, which then guides the search for where to look next for our new angles, theta 1 through theta n, in the next iteration. And that's all it is. We just repeat. So this is the point where we're going to switch to the demo. So if you can all go ahead and open up on your Jupyter notebooks the file called vqe_demo.ipython notebook. And if you haven't been able to get your Jupyter setup up and running, you can just find someone who has theirs up and running and you can work as a team. And we're going to be running a little competition where the winner is going to get credit from the IBM Quantum Cloud. And I'll tell you a little bit more about that later. And the first thing that you should do on this Jupyter notebook is just to run this setup step. So to run a cell, a Jupyter notebook is a bunch of cells. You just click into the cell and click this run button. And this is actually going to fail. It's going to print ISCA 2818 tutorial token setup fail. That's fine. That's because we don't have the IBM dedicated cloud service today, but you can set that up later after this tutorial. So everyone should run this cell and you'll see API token setup fail. So let me go over again what this algorithm is. So we're going to run the variational quantum eigensolver to try to find the ground state of the hydrohelium molecule, which is helium connected to a hydrogen ion. So everyone's opened up the VQE demo notebook, and you've run this step. It should fail. That's expected. That's fine. And just to reiterate, what we're doing is we're finding the lowest eigenvalue of a matrix H, and our procedure is guess, check, and repeat. So in the quantum part is where we do the guessing and checking. The guess means we prepare an ansatz, a trial qubit state, that's our guess, and it's parameterized by n angles. The check is where we measure the energy, the Hamiltonian, term by term. And then the repeat part is the classical. That's where we pass the results to a classical optimizer. In the competition demo, you are going to be the classical optimizer to guide the next angles. And then we just repeat. So the key question behind how VQE works is how do we guess intelligently? In other words, how do we prepare the ansatz? And there's two ways we can go about this problem. The first is something called a problem ansatz. So what that means is we take a look at what kind of problem are we trying to solve and think about what does the underlying chemistry or the underlying physics tell us about what guesses are good. And in the case of quantum chemistry, the gold standard for guesses is called UCC, the unitary coupled cluster. But then the other way we can think about this is to do a hardware ansatz. So that's something that maybe is a little bit more beloved to architecture folks. And that just means let's take a look at the quantum system that we're running our program on. What kind of gates is our quantum system really good at implementing? It's either really fast or low error, et cetera. And let's just build some sort of guessing system that is really well adapted to the machine that we're running on. And that's what we're going to do for this demo. We're going to pick a hardware ansatz that was proposed in 2017. And this is a particularly good ansatz on a certain class of machines. So this is what the circuit for that ansatz looks like. And I'll try to convey some intuition, but I'll also point out that an ansatz is a total guess, especially a hardware ansatz. There's not too much rhyme or reason to it. It's just meant to have a lot of free parameters so that it can explore that exponential state space in ways that a classical computer can't. And it's parameterized by 10 angles that you can see here. So in the first step, we have 4 angles. We do x rotations and z rotations on that block sphere that describes the quantum bit. There's 4 angles, alpha 0, alpha 1, beta 0, beta 1. The second step is the entangler. So if you recall, the C0 gate creates entanglement, and that's exactly what we have here. If we didn't have C0 gates, then this could be just thought of as like separate qubit lines. There's no interaction between them unless we have an entangling gate like the C0. And then the last step is just more rotations. There's 6 more angles here, gamma, delta, epsilon. So what we're going to implement this is called Scaffold. It's our C-like quantum programming language. And we built a Python interface around it, so you're just going to input it as if it's a Python string. So if you scroll below the API token stuff, you'll see the skeleton of the code. So there's a main function which declares 2 qubits as our registers, and then 2 classical bits, which are C bits, as a result. And then we have just 2 steps. Prepare the ansatz, which is guess, and check it, which is measure. and we're going to implement those. So digging into prepare ansatz, I broke down prepare ansatz into 3 steps. Step 1 is the initial rotation, step 2 is entangler, step 3 is final rotations. So in step 1, the code is ready for you. All it does is it implements this gate diagram. So it performs X rotations and then Z rotations. The first argument is the qubit that we're operating on, and the second argument is the angle with which we want to rotate. The second step is where you're going to write code, and this is the entangler. So it should be empty for you, but you want to go ahead and implement step 2 of this circuit. And the solution is here. You want to apply a Hadamard on the top qubit, which is reg 0. You want to apply a C0 to control on the first qubit and target on the second qubit. That's the order of these arguments, control, comma, target. And then you want the Hadamard on the bottom qubit, which is reg 1. And then you want the C0 with the control and target reversed. So you can either just follow along here, or if you scroll to the bottom of the Jupyter notebook, then you have the solution here too. You just have to run this cell, the entangler, and you can copy and paste that too. So I'll give everyone like 30 seconds more to write out that code. The next step is the final rotations. This one's kind of tedious, but you can go ahead and either look at it here and implement it, look at the circuit directly, or there's a solution cell for it right below the entangler one. And this is just implementing the Z rotations, the X rotations, and then the Z rotations again. So that one's already there. Then the last step is to do the measure. So the question is, what does it mean to measure this H matrix? Well, it turns out for the molecule that we're interested in, hydrohelium, that's the Hamiltonian, the H matrix. And the way we would actually measure this is doing it term by term. There's 9 terms, and we can measure these terms, which are expressed in terms of Pauli matrices, pretty easily. And we're only going to implement one of these terms. The one that we're going to consider has the coefficient of negative 1.0467 sigma zi. And the reason I picked that term is because it's, I'll skip over the details here, but it's the easiest term to measure. All you do, you don't have to do anything special to measure it. You just measure it, and the way you consider it to have an expectation value is if you measure 0, 0 or 0, 1, the outcome that you consider is +1. If you measure 1, 0 or 1, 1, the outcome is -1. And there's a cell that'll actually just tabulate these counts for you, measure the fraction of times that you got 0, 0 or 0, 1, measure the fraction that you got 1, 0 or 1, 1, and then figure out the average for you. So you don't have to worry about that. But you will have to write just the code. Oh yeah, and one thing to mention is that normally we want to minimize the ground state energy, but the coefficient here is negative, so we actually want to maximize the result of our measurement here. So in terms of code, this is what it looks like. Again, because we're picking the easiest term to measure, all we do is say result 0, which is the classical bit, is equal to measure z of reg 0, which means measure the top qubit, and then measure the bottom qubit. So again, you can copy and paste this from that solution cell or write it up from here. And once you're done with this, we'll be ready to actually run this. So everyone should now have your scaffold code in this cell. And if you run that cell, that'll store in that scaffold code variable. And then the next part is to actually execute this. So to execute it, we want to convert this to quantum assembly. So if you run this cell, compile the scaffold to OpenChasm, and run it, you should get something like this. And actually, if you scroll all the way to the bottom, you can do the circuit visualization and run this cell, which will show, okay, I've got some import issues, but hopefully on your computer it should show a circuit. The next part is to actually run this, which is this execute on a simulator step. So if you all run this, you'll get a histogram of what did we measure. And it turns out, since I just picked angles of 0 for all of my alpha 0 through epsilon 1, this circuit is basically doing nothing, which means that we just get with equal probabilities 0, 0, 0, 1, 1, 0, 1, 1. And that means that the expected value is basically 0. So this is where the competition part comes in. If, just as a reminder, VQE has this classical step where we go back, we take a result, and we change the angles. So for example, I might do alpha 0 equals 3, beta 0 equals 2. These are angles between 0 and 2 pi. I'm going to run it again, compile it again, and you'll see that I have new angles for my Rx term. And then if I run it again, I'll now see that I have negative 0.03. So we have 5 minutes to run this as a competition, and if you have any questions, you can raise your hand. But the competition here is to do the following. It's to maximize the expected outcome here. So what you're going to do is basically play the role of a classical optimizer and change the values of these angles, alpha 0, alpha 1, through epsilon 0, epsilon 1. And you want to maximize the output of this cell execute on a simulator. And the winner of this is going to get 100 credits from the IBM Quantum Experience, which actually means that 100 credits are replenishing. It means that you have a really big bandwidth with which you can actually run real quantum programs. And then second place is going to get 50 credits, and we'll work out the splitting of credits between teams if that happens. But are there any questions about this process? The largest positive value that you could get is +1. So you want to get as close as possible to +1. I just want to say two things. One is that if you had issues with the IBM QuizKit backend, just try restarting your kernel, and that seems to fix it. The other is someone asked, is there any intuition behind this circuit? What are these angles? And there's kind of two answers. One is that one really important part here is that we have entanglement. Otherwise, we don't really have a 2-qubit system. We just have 2 separate lines. The other piece is we need enough free variables, like enough slack in the system, so that we can explore a really wide range of possible state vectors. So that's why we need like 10 angles here. As to why these specific angles and why these specific orders are chosen, like why it's X then Z, that's more of an art than a science, and it is really just a matter of what this paper proposed as being really easy to implement on their machine. So the other answer is there's not that much intuition to it because this is a hardware ansatz. It's just meant to be really efficient on their machine. If you do, you can kind of game this search, by the way. Instead of just trying random values, another way, if you had some quantum background, is to reverse engineer this circuit to make it try to print out at the end only 1, 1 or only 1, 0. So that's another way you can try this approach that's a little bit more intelligent than guess and check. But historically, guess and check works really well. So hopefully some of you might be achieving like 0.4 or 0.5 or higher. Has anyone beat 0.5 as an expectation value? Awesome, there's some people. I will note there's actually a bug. If you're too good, then there's a bug because we expect there to be some non-zero counts of 0, 0, and 0, 1. So if you want to fix that because you're doing so good, you should replace that with like a counts.get with a default value. But it's rare to run into that. You have to be like really cutting close to the 1.0 maximum saturation. All right, that's time. So let's do the reveal of our numbers. If you beat my score of negative 0.03, please stand up. Oh, wow. OK, so I think we have our 2 winners. Do you just want to like come up front and take a photo, and then we'll remember you?
As we mentioned, you can follow our Twitter handle, but in particular, if you're interested in the software and software updates, probably it would be good to follow our Twitter handle.